Once safety requirements have been identified, analysis is used to determine if the system design meets those requirements. A failure mode effects analysis, or FMEA, is often used to deal with hardware faults in system reliability. An FMEA starts by hypothesizing that a hardware fault occurs. It then works forward from the known particular failure modes of that particular component to see what mishap might result. FMEAs are helpful, but quite limited for safety because they do not deal with multiple fault scenarios, they do not represent correlated hardware faults, and because software can fail pretty much any way it wants, so an FMEA's assumption that software fails in known ways often does not work for safety. For safety, a fault tree analysis, or FTA, is also required. Fault trees work by starting with a mishap or hazard and working backwards towards the possible causes. Here's an example showing that a fault tree is kind of drawn upside down, with the root of the tree at the top and the leaves at the bottom. In this example, a hazard or mishap is at the top of the tree, at the root, and working downward toward the leaves. There are nested levels of AND gates and OR gates. An OR gate means that any one of the inputs below will, if true, cause the hazard. An AND gate means that all of the inputs below that gate must happen concurrently for the hazard to be caused. With this formulation, it becomes clear that AND gates are good because a single fault cannot produce the hazard if it goes through an AND gate. On the other hand, OR gates are bad because they document multiple potential ways for a hazard or a contribution to a hazard to occur. This insight from fault trees leads to the conclusion that for life-critical systems, you must have no single points of failure. That, in turn, means that a fault tree must have no paths from a leaf to the root that passes only through OR gates. If all paths go through at least one multi-input AND gate, then there's no single component that can cause system failure. More generally, considering a single point of failure is asking the question, if a single component breaks, is the system unsafe? And that question has to be asked of every component in the system. Asking this question can be subtle and tricky in practice, because when a component breaks, it does not necessarily just go silent. Rather, and especially with computational elements, a component failure can happen in the worst possible way for the system. In general, there is no way to guarantee that software will fail in a well-behaved way. Thus, software failures have to be presumed to do their worst to try to make the system unsafe. For our vehicle speed control example, any single computer in the system must be presumed to fail, for example, commanding full engine power, which is unsafe. That's why a safe engine controller has two computers working in tandem, so that if one of them fails, the other can at least perform a system shutdown. In practical systems, avoiding single-point failures is a start, but not quite enough. There may also be likely sets of correlated faults that affect multiple components. Additionally, independent failure arguments generally don't work for software, so software on two different components might fail in the same way. That's handled by developing software to the highest SIL needed for the system and ensuring that, for practical purposes, the software is perfect in that it will not exhibit unsafe behavior.